So the type of the permutation given by the product of these cycles 1, 3, 7, 2, 4, 5, 10, 9 and 6, 8, 11 is is of type 1, 0, 2, 1, 0, 0, 0, 0, 0, 0, 0, right? So why is that? Well, there is precisely one one cycle. There is no two cycles in this. There are two 3 cycles 1, 3, 7 and 6, 8, 11. There is one 4 cycle 2, 4, 5, 10, and there is no other larger cycle. So all these values up to 11 are going to be all zeros. You cannot have anything larger than 11 because the number of elements is 11. Now, once you have such a type, right? So then we can define the cycle indicator monomial, right? Of pi given by, let's say, z pi is equal to z1 raised to c1, z2 raised to c2, etc., zn raised to cn. So this tells immediately what is the cycle structure, right? Look at the coefficient of zi, that will be telling the I cycles, right? And not the coefficient, the exponent of zi will tell you the number of I cycles. So, given now a group of symmetries, let us define the cycle index polynomial of the group as Zg is equal to Zg of let's say Z1 to Zn, right? It's denoted by G of Z1 to Zn. Is 1 by order of G, summation over all the permutations in G set pi, right? So the sum of all these monomials, right, normalized by the order of G, right? So this is the cycle index polynomial of the group G. So this will be very useful. We will see how this cycle index corresponds to the counting of colorings that we are going to do. So as an example, let us say that we have the 4 cycle X with the vertices A, B, C, D, and look at the group of rotations of the cycle, right? So what is the cycle index polynomial? So Zg is 1 by order of G, which is 4. Now Z1 raised to 4. Why is it Z1 raised to 4? Because there is the identity has exactly 4 cycles, right? Then Z2 raised to 2, because you look at the generator, the square of the generator, you will see that you will have 2 cycles of length 2, so it is Z2 raised to 2. And then you will get 2 times Z4, because you will see that the generator and its inverse are 1 cycles, so are 4 cycles, and there are 2 of them. So that will tell you this this cycle index polynomial is 1 by 4 into Z1 raised to 4 plus Z2 square plus 2 Z4. Okay. Now, as a homework, you can look at the example to find ZH, where H is the rotations and reflections. Okay, so instead of just the rotation, suppose we also allow reflections, then we will see that Zg is actually equal to ZH will be whatever it is. So find that as a homework. We come to the main theorem that we wanted to prove, which is Polya's theorem. So Polya's theorem, again, as we noted before, what we wanted to do was to count, inequivalent colorings where the number of colorings is given, right? So let X be an n-element set and G be a group of symmetries of X. Now, let us consider a set of colors C, which is R1, R2, etc. Going on, right? Whatever, some set of colors. Now, it could be finite or infinite, but we will just take it to be infinite at the time being. Now, look at the number of inequivalent colorings under the action of G, where the color, let's say Rj, appears exactly Ij times. Okay, so that is denoted by eta of I1, I2, etc. So eta of I1, I2, etc. says that, okay, color R1 appears I1 times, R2 appears I2 times, etc. Rj appears Ij times, right? So look at the such colorings and then see under the action of the how many inequivalent colorings are there. Okay. Now let us define Fg of R1, R2, etc. Right, where the the colors are the variables of the Fg. A summation over all the tuples. I mean like I1, I2, etc. Right. Eta of I1, I2, etc. R1 raised to I1, R2 raised to I2. So which means that the coefficient of R1 raised to I1, R2 raised to I2, etc. Right, is the number of inequivalent colorings where Rj appears Ij times. And sum over all these, and you will get this polynomial, right? So if you look at, I mean, it need not be a polynomial. If C is finite, then it will be a polynomial. If it is not finite, then you will get a power series, right? So you will see that this is basically a generating series, and then we can look at this and the coefficient of this in the series. This time in the series will be precisely the number of such colorings, right? Inequivalent. I mean that is the generation of the that is the definition of the generating function. Then Fg of R1, R2, etc. right, is actually equal to the cycle index Zg, right, of the group, cycle index of the group Zg, where Z set I is substituted by summation R Rj raised to I. Okay, Z I is substituted by summation Rj raised to I. So Zg of R1 plus R2 plus etc. Comma R1 square plus R2 square plus etc. Comma R1 cube plus R3 R2 cube plus etc. Comma etc. Right. So this is what Fg is. So that is what the theorem says. The theorem says that there is a direct relation between the cycle index of the group, right, and the counting of this inequivalent colorings, where the number of colorings are fixed. I mean, number of occurrence of each color is fixed tuple. So how do you prove this? So to prove this, suppose I1 plus I2 plus etc. is equal to n, right? So of course, when we have only n elements, we cannot use more than n colors, right? So even though the set of colors is infinite, the tuple that we are going to consider, which is going to contribute anything, is going to be always adding to n, which is the cardinality of x, right? So let I1 plus I2 plus etc. equal to n, and ij is of course greater than equal to 0, and the tuple I1, I2, etc. is denoted by I cap. Okay. Now let us say that C I cap denotes the set of all colorings where the number of colors, number of times the color Rj appears is exactly Ij. Right. So as I mentioned before, the permutations can only take such colorings, in the colorings in Ci to again colorings in Ci, because the number of times a color occurs cannot be changed by the permutations, right? So therefore we can see that the group G, whatever is the symmetric subgroup of the symmetric group we are taking, that group G acts on on this the restricted coloring Ci cap. That is that any permutation pi if you take, and any coloring in Ci cap you take, right? Pi dot f is again an element of Ci cap, and so this action of the restricted action of this group, right? I mean of each of these permutations, let us say it's denoted by pi I cap, right? So the action of pi on ci cap is denoted by pi I cap. Because pi acts on each of so for each I cap ci cap basically gives a partition of all such colorings, and then for each partition, the permutations acts within that partition, right? So that is what we are saying before. So let pi I cap be this particular action of pi on I cap. Now we want to apply Burnside's lemma, so therefore we want to find the cardinality of fix of pi I cap. Right? Now how do you find the cardinality of fix of I cap? So if you look at any coloring, then this coloring is fixed by pi I cap only if the the cycle structure of pi is such that, right, in any cycle of pi, all the elements get the same color by this coloring f, right? So if you are looking at a coloring f, then all elements of this particular cycle that we are looking at pi should be given the same color by the f, right? Otherwise, when you rotate it, it is going to give a different color, right? So therefore that will be the same, and of course, the color rj must appear exactly ij times, because by definition, right, I in I cap, the action of pi in I cap is going to basically map a set of vertices with the same color to some other set of vertices, right? Exactly the same number. So with this observation, let us define h pi to be the product over all j, r1 raised to j, r2 raised to j plus etc. whole power cj of pi, where cj of pi is the number of j cycles in pi, right? So pi is the permutation which is acting. Then correspondingly, we define h pi to be the the polynomial product r1 raised to j plus r2 raised to j plus etc. whole raised to cj of pi over all possible j, right? Now let us see what happens in this x pi, right? See, when you take the expansion of this product, right, you will get different monomials, right? That is what the polynomial is, right? It's a sum of monomials. Now, how do we get one of these monomials? So to get a monomial like this, we have to choose some term, right? Let's say some r k raised to j from each of the factors, right? So each factor in this product, we have to choose some element, right? So when you expand out, right, all these things, or over all the j, you write r1 raised to j plus etc. into r1 raised to j plus etc. cj times. Then like this for j is equal to 1, then j equal to 2, j equal to 3, etc. Right? So we do this for all possible j, and then we get this huge product of different sums, and then a monomial in the whole product is going to come from by choosing some rk raised j from each of these terms, right? Now, what is the choice of rk raised to j says? Rk denotes, right, it is a variable which denotes the color rk, right? So rk raised to j says that some j cycle, right, is colored with rk, right? All the elements in some j cycle is getting the color rk. Now we know that in this product, right, we have exactly cj times. You can take some some ri raised to j. We can choose exactly cj times, right? So therefore, choosing a term like of the type rk raised j from every factor says that we are going to color the set x that we are coloring, right, such that every cycle, right, is going to be monochromatic, right? That is what it comes to. So all elements of the cycle get the same color, right? That every cycle is monochromatic. Now the product of these terms will be some monomial, right? Like something like r1 raised j1, r2 raised j2, etc. Where we have used the color rk a number of jk times, right? So this corresponds to whatever monomial we are looking at. Now it follows that the coefficient of coefficient of this time that we are looking at r1 raised to j1, r2 raised to j2, etc., is actually equal to the number of permutations, number of elements fixed by the permutation pi I cap, right? The action of pi is pi I cap, right? So that by this action, how many? What is the fix of pi I cap? That is precisely the coefficient of r1 raised to j1, r2 raised to j2, etc. So that was the claim that we want to make. The coefficient of r1 raised to j1, r1 raised to, let's say, i1, r2 raised to i2, etc. in S pi is fix of pi I cap. Right? Now, so therefore, we can write h pi now as summation over all I cap, right? The cardinality of fix of pi I cap with the with the monomial r1 raised to i1, r2 raised to i2, etc. Right. So this is what s pi is. Right. This is what we just argued right before. So now we can apply the result, that is 1 by order of g summation over all pi belongs to g s pi is actually equal to summation over all pi belongs to g product over j, right, which was the h pi was written like this, r1 raised to j plus r2 raised to j plus etc. c j pi. Now what is this, right? This is set g of r1 plus r2 plus etc. r1 square plus r2 square plus etc. Yeah, so for substituting for each ri with r1 like what like yeah, so the first time with r1 plus r2 plus etc., second time with r1 square plus r2 square plus etc., and going on, right, like this. But now this is summation overall, this is summation overall I cap, right, like where I so writing this in another fashion, we can write is a summation overall I cap 1 by order of g summation overall all the permutations in g cardinality of fix of pi I cap x1 raised to i1, I mean not x1, right, what was that, r1 raised to this is supposed to be r1 raised to i1, r2 raised to i2, etc. Why is this? uh, because we are substituting for h pi, right, is equal to h pi is equal to summation over all I cap or order of fix of pi I cap r1 raised to i1, etc. In this identity, right? So by substituting that, we will get this. But now, what is the coefficient of this term in this summation, right? This is by Burnside's lemma. This is precisely the number of orbits of pi I cap, right? That is how the Burnside's lemma was stated. So therefore, this is precisely the number of inequivalent color rings using color Rj total of Ij times, right? So that is what the coefficient of the monomial means. So this is what we wanted to prove, right? So we proved Polya's theorem by as an application of Burnside's lemma. Okay, so what we proved is that the number of inequivalent color rings, right, where the number of times the color Ri occurs is given by the tuple I1, I2, etc. is obtained by obtained by looking at the cycle index polynomial of the group G, right, Zg, And for the variable, for the variable zi, I replace it by summation rj raised to I, right? So this will give you the uh, the generating function of this kind of coloring. Right? So that is what Polya's theorem is about. So now let us look at some example. Right? Go back to this, make sure that you understand the theorem well, and then we can look at the example. So one of the standard examples that you give is that of counting of necklaces. So a necklace of length L is, I think we mentioned this in one of the classes a long time before. It's a circular arrangement of, let's say, colored beads. So we were looking at another type of necklaces that time, where instead of beads we were using cowrie shells and something like that, which is slightly different in some sense. But for the time being, we have uniform circular beads. So we have a circular arrangement of these beads, and we will assume that when we make the necklace, the distance between so in the circular necklace, the distance between any two is the same, so that you get a regular regular polygon with L vertices, right, as the necklace. Now, two necklaces are the same if one can be obtained by a cyclic rotation of the other, right? So this is something that we will assume. This is the group action that we have, the symmetry. Then the number of inequivalent n-colored necklaces. If you are going to color the necklaces, the beads with any of the n colors, it is given by 1 by L summation over all d that divides L, phi of L by d, n raised to d. Okay? So this is the claim. Okay? So the number of inequivalent n-colored necklaces is given by 1 by L, where the length of the necklace is L, summation over all d dividing L, right? So all the divisors of L. Phi of L by d. Phi is the Euler function. So L by d is, of course, because d is a divisor, L by d is an integer again. Now for this integer, look at the Euler, the number of numbers less than that and coprime to it, right? So where the GCD of that number and L by d is 1, right? So that is the Euler phi function, which is the coefficient of n raised to d. So this is what we want to prove. How do you go about proving this? So if you want to apply Polya's theorem, we want to look at the cycle index of the group. So let us find the cycle index of the group that we are looking at, right? The group is the group of rotations, right? So for the L cycle. So let us say that our set is the set of elements 1, 2, etc. L is the set of beats, and the group of rotations of the necklace are generated by the permutation, because as we mentioned, the rotations are generated by the single permutation, which is given by 1 going to 2, 2 going to 3, etc. Up to L. So if this is the generator, then the group G is given by 1 comma pi square, etc. pi raised to L minus 1, where pi raised to L is equal to 1, right? Identity. Now, what is the cycle structure for permutations in G? So this is a very interesting example. So can you think of some nice properties of the cycle structures of the permutations in G, right? So if you are looking at the group of rotations, what can you say about cycle structure? So it turns out that if you take any permutation in G, there will be there will be several the number of so there is only one cycle type, cycle of some length, and that will appear many times. Okay, so all the cycles in each of the permutations will have the same length. That is what I wanted to say. So all the permutations will have the same length. So can you think of why? Okay, so or can you prove this is true, right? For every permutation in G, all its cycle lengths will be the same. So if you write any permutation in G as a product of cycles, then all the cycles will have exactly the same length. So prove this. So so why is this? So well, if you look at the rotation and then try to represent it as using some modulo arithmetic, you can easily prove this. And observe that like if sigma is pi, where pi is the generator, pi raised to m, then sigma has exactly GCD of m comma l cycles of length l by GCD of m comma l. So this is an even more refined claim. So prove this. Now once you have this, we can apply Polya's theorem, right? Polya's theorem says that once you have the cycle structure, we can directly apply this, right? So therefore, I have 1 by L summation, m equal to 1 to L, n raised to GCD of m comma L, in equivalent, colored necklaces, right? So this is by Polya's theorem. But what we know is that GCD of m comma L is equal to D if and only if, right? M1 less than or equal to m by D less than or equal to L by D, and GCD of m by D comma L by D is equal to 1. Okay. So using this, we can write this same summation as sum over all the divisors, right? So sum over all the divisors of L, 1 by L summation D dividing L. Now n raised to D, how many times it appears? It appears exactly pi of L by D times, because those many times will be, those many numbers will be coprime to coprime to uh, uh, coprime to what is that? Coprime to D, right? So therefore we get we can write this as in this form. And now, so this is what we were asked to prove. What was it? Yeah, so this is what we were asked to prove, right? Now, as a further observation, the property of the cycle structure of the permutations in G, we have the cycle indicator, right? Zg of Z1, Z2, etc. Zl is written by 1 over L summation D dividing L, pi of L by D, Z raised to D, ZL by D whole raised to D, right? This again directly follows from the property of the cycle structure, because all the other terms will be disappearing. They will not be here, right? So therefore, we will get exactly this. And but now I can write it also as 1 by L summation D dividing L, phi of D, ZD raised to L by D, because I'm just exchanging D and L by D, because they are just divisors. If D is a divisor, L by D is also divisor. So I can write it in either of these forms. So we will see that the connection between ZG and the and this form, right? So it follows that Fg of R1 R2. So we wanted to find out Fg, right? The entire generating function we want to find out. We can write Fg of R1 R2 etc. as 1 by L summation D dividing L, pi of D. Then you replace this ZD by the corresponding R1 raised to D plus R2 raised to D plus etc. We said that Zi is replaced by R1 raised to I plus R2 raised to I plus etc. So in this case we have only ZD. So we have R1 raised to D plus R2 raised to D plus etc. whole raised to. So this is how we use Polya's theorem. And here are some homework questions. Show that summation overall D divisors of L, pi of L by D equal to L. And the second question asks you to show that if we allow flipping of necklaces as well as rotations, right? Instead of the just rotations, we also allow flipping or taking mirror images. Find the cycle indicators and the colored necklaces. Okay. So try to solve this question. And the third question is that you want to count the inequivalent colorings of a set of L elements using n colors under the action of the entire the full symmetric group Sx. Then show that if summation I times Ci is equal to L, then the number of permutations in Sl, right, with the Ci cycles of length I is given by L factorial divided by 1 raised to C1, C1 factorial, 2 raised to C2, C2 factorial, etc. etc. So these questions are your homework questions. So with that, we wind up the topic on Polya. We can do more on this, but let us stop with this for the time being. I will try to give you more questions if you want. There are several interesting questions one can, but at the moment these are your homework questions, and then I will come up with more questions and send you soon.